We look at some other types of situations where static indeterminacy is something we can deal with using our new relative displacement equation. So these are going to be some extra types of problems that we can apply displacement in order to help out what's going on with equilibrium. And are officially on assignment of 4B. Uh, so yeah, basically just what I said. Are we talking about thermal displacement in this video? No. Why is that on there? Okay. Note to self, gonna take care of that. Uh, so again, this is just all going to be static indeterminacy. I think I added some extra examples. So thermal displacement is going to be in our next video. Ignore that. What is happening? Everything's rebelling. Okay. We're only 13 videos in. We can't afford to have rebellion now. Let's take a look at this question. I really like this as a discussion that we have in class. So I guess kind of take some deep thinking on this one. But we have a concrete pillar that's reinforced by bonding it with 8 different steel rods. We're applying a 200 kip force along the top, and we want to know, based on comparing both the steel and the concrete, what is going to be the same in this situation? So these are all things related to our displacement equation, our normal force, our initial length, our area, our modulus of elasticity. So go ahead and pause here and think about what's going to be the same for both the steel and the concrete. Okay, so hopefully you've done that. I usually will kind of do this one at a one by one and have a discussion, and we'll kind of chat about it as a class, which we can't really do here. But I think there are some things that are going to be easily not the same, right? I think if we're thinking about steel and concrete, they're both going to have different modulus. The modulus of, let me say this so I don't have to worry about the plural form of modulus of elasticity. The modulus of elasticity for steel and is going to be different than the modulus of elasticity for concrete. They're two different materials. They're going to behave differently. So we know it's not D. We can see looking at this that the initial length is going to be the same. Um, yeah, because they're all 3 feet to start. I don't know why I looked at that like that was going to give me a problem. I have it boxed in my notes, so I know what the answers are. I've already thought about this. Um, The other thing that I think is very easily going to not be the same is going to be the area because we've got the area for the steel is going to be different than the area for the concrete. So that takes that off of the list. Now, what's left, if we're thinking about this, is going to be our displacement and our normal force. Well, displacement is going to end up having to be the same because the steel's not going to move more or less than the concrete moves. They're going to have to move the same amount, which kind of brings us to this question, right, of what's going to be happening with the normal force. But if the length is the same and the displacement is the same, but we have two different materials with two different areas, like just looking at this equation, here, let's do it this way, actually. I think this will help. So we have 200 kip acting downward. We have the normal force for the concrete. And I guess we can think about it as kind of 8 different steel shapes. So we could do 8 times the normal force for the steel. But looking at one rod, the concrete and the steel, if we just assume that they're different, N concrete times L over AE, for both of those being for the concrete. And then if we think about one steel rod, the normal force in one steel rod over the area of one steel rod times the modulus elasticity of steel. The lengths are going to be the same. And because the areas, the A's and the E's are all different, then the normal force is also going to have to be different. There's no way that the normal force in those is going to be the same. So the normal force is going to be different. And that's something that we want to kind of keep track of and why, as we're starting to do these free body diagrams, when we have these materials that are bonded onto other materials, we're going to want to account for the fact that we have different normal forces. Just like we did here, we would have eight normal forces for our steel because we have eight different steel rods. You can do this a couple different ways. Um, you can think about the displacement as for all of them, so you can just have eight times the area here, or you can, in your equilibrium equation, have eight times the normal steel force. It's either or. You either think about this as one rod, and then you would have eight in your free body diagram, or you have one end steel force in your free body diagram for the collective steel, and then you have eight times the area in your equation. I like to do it this way, so I'm going to do it this way. Cool. So this is kind of a good setup for one of your assignment problems. Oh, it says that right up at the top. Um, this is I don't know if the numbers are the same in the 15th edition. I'm assuming they are. So there's that. Everything that we do in the notes is from the 14th edition because that's what I built this with. I don't want to redo all of my notes just because the textbook company wants to like make more money by having a different problem set. Okay. So, this is another setup for, I think, your coding project, if not on your assignment, but this is one of the things you're going to be looking at in coding project 3. Yep. We have a 2014 T6 aluminum rod AC being reinforced firmly with the firmly bonded A992 steel tube BC. If the assembly fits snugly between the rigid supports, so there's no gap at C, we want to determine the support reactions when the axial force of 400 kilonewtons is applied. The assembly is attached to D. So up at the top, it's attached to D. There's 400 millimeters of just pure aluminum. That's the aluminum. Uh, and then after that, for the last 800 millimeters, we still have the aluminum rod, but it's now got this steel tube bonded around it. The aluminum alloy has a radius of 25 millimeters, and then the steel tube goes out to 50 millimeters for, again, that bottom 800 millimeter portion. And then C is at our bottom where it's going to be fixed there. It looks like there's a little gap, but that's because the next problem does have a little gap, but we don't have a gap here. So we're just setting this up because this is going to be a problem that you're going to be kind of working with these equations for your coding project at the very least. So one of the things that we want to do first is take a look at what is going on here. So sketching this out, just like the problems that we were doing, I almost said yesterday because I was recording the video yesterday, but in the last video, we're going to think about sketching out our free body diagram here, adding in some forces for our supports. We have FD, which I'm going to draw up to kind of oppose that 400 kilonewtons. And then at the bottom, we've got the force at C. But that force at C, because the steel and the aluminum we've just kind of established are going to be having different internal forces, they're going to have different forces at the supports too. So that's going to be our F steel plus F aluminum if you think about kind of the summation of the two of those. So if we're going to apply equilibrium like we did in our static and indeterminate problems yesterday, we have the summation of forces in the y direction is equal to 0. It's going to be FD minus 400,000. Then it's going to be plus F steel plus F aluminum. So that becomes our first equation here that we have to work with. So that's going to be our equilibrium equation. Yep. Uh, right. And that's what we would get if we were kind of doing any particular slicing anywhere. So we will also, because just like we did the other day, if we want to think about displacement, we're going to want to think about slicing through these sections to kind of get some equations here. So doing that, right, the next thing that we did was apply our displacement equations, which we're going to need two of because we have two unknowns here. Well, we have three unknowns total, but I have one equation already. So we're going to apply displacement. And we want to know because the end at C is fixed, that means the displacement from A to C is going to be zero. So I'm going to look at the displacement in the AB region plus the displacement in the BC region. Letters are hard. I don't like this is different than they labeled them the other day. That's what got me. C was in the middle for the other two problems. So I want to sum up the displacements in these two regions. And typically we would be able to do that pretty easily, but in this BC region now, we have two different materials, so we need to think about what is going to be going on with that. And at the very least, we need another equation because we want to think about the way that those materials are going to behave with each other. And just like in our previous problem, because these are going to be firmly bonded, that gives us our other equation, right? We can say that if the steel and the aluminum are firmly bonded to each other, that they're going to displace the same amount. So this becomes kind of our third equation that we're going to be able to get to use. So the displacement in BC for the steel is going to be equal to the displacement in BC for the aluminum, which means that we're going to have F steel times 0.8 for that length over the area of steel times the modulus of elasticity for the steel. That has to be equal to the force for the aluminum times 0.8 over the area of the aluminum times the modulus of elasticity for our aluminum. So this becomes our second equation here. And we can use that information to go back up to the first. So we're just going to highlight because I like highlighting stuff to keep track of things. We have our first equation, which was our equilibrium equation. Okay, so the reason we can use that is because if we're looking at the displacement from A to C, and the displacement for the steel and the aluminum is the same, I only need one of them, right? So we can be strategic here about which one we want to use for that region, the aluminum or the steel. And it becomes particularly easier if we think about it in terms of using the aluminum in that region, because then our denominators are all going to be the same. Let me show you what I am talking about. So if we're slicing in that first region to get our internal loading for NAB, our internal loading in that region is just going to be equal to that force up at the top. Looking in that lower region, we see that our force is going to end up being in compression for the aluminum, so we're going to account for that. But our displacement for AB is going to be FD times 0.4 over the area of the aluminum times the modulus of elasticity for the aluminum. We're going to add that to the displacement in BC, which we know is in compression. So we're going to bring in that extra negative sign. We're going to have a negative F aluminum here because that's what I called it, right? The normal force in the aluminum is just going to be the aluminum part times 0.8 over the area of the aluminum times the modulus of elasticity of the aluminum. And you can see how we can already cancel out that denominator because we chose to use the same material. You don't want to put both the aluminum and the steel in here when you're summing up the displacement because they have the same displacement in that region and you would be double counting it. You would be basically adding in that displacement twice because you would be doing it for both the steel and both the aluminum. You only need to do it once because that whole region is displacing once. Hopefully that makes sense. You can kind of use these equations to solve the rest of your coding project for that assignment. The second problem does some thermal stress stuff with the next video, so we're not completely done with it yet, but this is for that first problem. Just to kind of give you a picture of what this looks like in more detail, I have an extra example here. That's a little bit more complicated just to give us some additional practice. So we have a 10 millimeter diameter steel bolt surrounded by a bronze sleeve. The outer diameter of this sleeve is 20 millimeters and its inner diameter is 10 millimeters. The yield stress for the steel is 60 megapascals, and for the bronze, the yield stress is 520 megapascals. We want to determine the magnitude of the largest elastic load P that can be applied to the assembly, and we have the modulus of elasticity for steel is 200 gigapascals, and the modulus of elasticity for bronze is 100 gigapascals. So you can just see here a very simple picture of this bolt covered by this bronze sleeve. There's a compressive force P on both sides pushing in. So this is similar to all of the problems that we've been looking at so far with static indeterminacy, except for the fact that it's got two materials, which is our thing for today. So our first step here, ignoring the fact that we're trying to find P, we're still going to approach this the same way that we've been approaching everything else. So we're going to slice and apply equilibrium and displacement. So we're setting up our equations that we would use to solve this because we can do that without knowing what P is. It's always useful to set up your equations first and then see what you can do with it. So if I'm slicing through the middle here, then I'm going to have two compressive normal forces, one for the steel, one for the bronze, because we know those normal forces are going to be different. That's going to give me at least one equation from net force in the y direction. If I choose up as positive, set it equal to 0, I have N steel plus N bronze minus the force P. The other thing that we know is that the displacement is going to be the same. So we have the displacement in the bronze is going to be equal to the displacement in the steel. So N steel times L, because the L's are going to be the same, they'll cancel out. We're going to put some numbers in here, pi over 4 times 0.01 squared, and then times 200 times 10 to the 9. Those are going to be my meters squared in gigapascals for steel. That's going to be, whoops, I wrote them on the opposite side. That's fine. Just kind of went for it. Look, it's fixed. Nobody noticed. So we have the normal force for the bronze times the length there. We've got the area for the bronze, which will be pi over 4. This is the tricky part for these problems, is that the area of the bronze is not going to use the diameter of the full 200 millimeters. So we actually have to look at the areas kind of subtracting each other out. So it's 0.02 squared minus the missing 0.01 squared on the inside, and then times 100 times 10 to the 9 for our pascals for our modulus of elasticity. So be careful with the area there that you're subtracting out the area that isn't there for the particular material, whether it's with the concrete in the first problem or the steel and aluminum in the previous problem. But you can see, once we cancel out the L's here, that this is going to give us at least two equations, and we want to figure out what P is, right? We have two different options for P. Normally, this would be solvable. Uh, if we knew what P was, we could figure out what the normal forces were, and then figure out the stress, which is going to allow us to go backwards. So we're going to make an assumption about which one we're going to think is going to break first, and then we're going to use that yield stress to figure out what the normal force has to be, and then use that normal force to figure out an option for P. So step 2 is going to be to assume. Uh, I'm going to say we're going to assume the failure of the bolt. You could choose to do the other one if you wanted. I actually feel like the bronze would probably like fail first, just intuitively, but we'll see what happens. We'll do both, right? We're going to assume failure for both, and then we're going to compare the resultant values of P. So, assuming failure of the bolt, that means the normal force for the steel, we're pushing it up to that yield limit. So the yield for steel times the area for our steel is going to be 640 times 10 to the 6 multiplied by our area for steel, pi over 4 times 0.01 squared. This is going to give us a normal force of, okay, I must have just labeled that wrong in my notes, 75,398.2 newtons. No, no, that's not it. That is the one for, I see where I wrote it. I'm sorry. So that's going to be 50,265.5 newtons. My bad. And then using our displacement equation, we can solve for n bronze. From displacement, and bronze is at 75,398.2, which then collectively from our equilibrium is going to give us P as 126 times 10 to the 3, so kilonewtons of a force. So this is one option for the applied force that would cause the steel to fail. We're going to also look at the failure of the sleeve. Same process, but I just want to show you kind of that you can do this backwards. Knowing what the yield stress is, you can see what force you can apply. So same kind of general process, and bronze here. We're now using the yield test for bronze, assuming that breaks first. They're not both breaking at the same time. That's super important. They're not both breaking at the same time. One is going to fail before the other. So you're not going to use these both of these normal forces to find P. Does not work. We're going to look at 520 times 10 to the 6 multiplied by our area, pi over 4, 0.02 squared minus 0.01 squared. This gives us a normal force in the bronze of 122 1,522 newtons. Then from displacement, we're going to get the normal force in our steel is going to be 81,681.4 newtons. So which we can use collectively to get a force P of 204 times 10 to the 3, so kilonewtons. So this is our second option for P. This is what causes the steel to fail. The top one causes the bolt to fail. And this would cause the sleeve to fail. So what is the maximum? What's the word? What's the question we want? What is the question? What's the largest load P that we can apply here? It's got to be 126. Anything more than 126 is going to cause our bolt to fail. So we're using the smaller value here. This is going to be smaller. So it controls. Controls is again that word that the book uses. It's going to be our controlling value for this. We're not going to go any higher than that. So just a different application of our static indeterminacy stuff. Again, using the fact that these materials are going to be displacing the same. What does this different type of problem look like here? So we set up our equations and then we made some assumptions and kind of followed those through. There is one other type of problem that we're going to take a look at that we can use static indeterminacy for, that is going to be related to some more rotational type things. So in this problem, we have a bracket held to the wall using an A36 steel bolt at B, C, and D. Each bolt is going to have a diameter of 0.5 inches and an unstretched length of 2 inches. We're applying an 800-pound force to this bracket about 2 inches from the wall. And we want to figure out what the forces developed in each bolt. We can see that Well, we're going to assume that no bolt is going to carry any sort of shear force, so everything's going to be kind of a normal tension type situation. We're not looking at any shear. The entire vertical force of that 800 pounds on the bracket is going to be carried by this kind of pivot toe at A. So that entire vertical force is there. Everything in the bolts is just going to be normal forces. Makes it doable. And the wall and bracket are rigid. A is greatly exaggerated deformation. A greatly exaggerated deformation of the bolts is shown. So it's kind of really showing it pulling away from the wall. We're just kind of figuring out what's going on there. So where the toe is at the bottom, bolt B is about zero point 0.5 inches up from there. 1 inch up from there is bolt C, and 2 inches up from that is bolt D. And we want to essentially figure out what the forces are in each of these bolts. Yes, the force developed in each of the bolt. All right, so step one, we're just going to take a look at equilibrium here, assuming we have these three forces in these bolts that I kind of sketched out already. We're going to have this 800-pound force at 2 inches, so we're going to end up just doing a moment about A here. That makes sense to me, right? That's kind of our point down here at the bottom, our pivot point, so we can use that for our moment. We have 800 times 2, which is going to be a negative rotation conventionally. Then we're going to have, just going down from the top, our force in D times 3.5 inches plus our force in C times 1.5 inches plus our force in B times zero point 0.5 inches. This gives us one equation. I have three unknowns, so I'm going to need two more equations, and I want to think about how the heck am I going to get those? And this is where we're going to be applying our displacement or our compatibility. The displacement here is going to work just like it was working in chapter 3, where we were thinking about the triangle stuff, except we're going to have one kind of pivot point at A. If we think about our vertical line up being the wall, we've got B, C, and D. And then we're going to exaggerate those displacements out. So we can look at the displacement from D to D prime, C to C prime, and B to B prime. So you can kind of see what we're going to be doing here. We're going to be looking at these ratios for these triangles. We need at least to compare two of these, which is completely doable. So let's take a look at D and C and D and B. Those are going to be our two different equations. So the displacement of D over 3.5 is going to be the displacement of C over 1.5, which gives us 1 over 3.5 of the force in D times 2 inches is my original length. We're plugging in that displacement equation over the area, and modulus of elasticity is going to be 1 over 1.5 times the force in C times 2 over the area modulus of elasticity. LA and E are all the same, so we just kind of get the ratios of the forces. Good to know. Our second equation can compare D and B. So we have the displacement of D over 3.5, displacement of B over 0.5, gives us again another equation, 1 over 3.5 FD times 2 over AE is going to be 1 over 0.5 FB times 2 over AE. AEs will cancel as well as the 2's. And then you just have three equations with three unknowns. So we can just go ahead and apply our math here. Not so bad, but I just wanted to show you that that type of displacement and using the ratios with the triangles is also something that we can use here to be able to compare stuff. So step 3 is math. Math. We've got FC is going to, I'm going to have to check the transcripts to make sure that that comes out as math. FC is going to be 163 pounds. FD is going to be 380 pounds. And FB is going to be 54.2 pounds. That brings us to the end of our different types of static indeterminacy problems, doing a little bit of extra work to solve some pretty neat problems. In our next video, we'll be finishing up chapter 4, talking about thermal stress as well as stress concentration. Um, so what happens when it gets hot and the beam wants to expand? We're going to get stressed that way too, kind of building off of our indeterminacy type of things. And then what happens when we have a beam that's got a hole in the middle or around fillets? That's going to be our stress concentration. So I will see you in the next one.